This video demonstrates how to do machine learning with CASP on various target platforms, and shows how to use accelerators on supported platforms to accelerate the machine learning process. For this demonstration, native PC with Opencl and CUDA supported hardware, Raspberry Pi 4 and Nvidia Jetson platforms are chosen. These platforms are made ready with required drivers and all dependencies installed before this demonstration. Respective CASP board support packages were also installed. For Raspberry Pi 4 and Nvidia Jetson platforms, CASP remote build feature is used to compile the model on the target platform itself. We use MNIST fashion dataset on all three platforms to train a simple 2-layer 64 neurons per layer feed-forward neural network. Please note that, the purpose of this video is to demonstrate how to do machine learning with CASP and not to compare performances across various architectures and softwares. We use existing tutorial project for this demonstration. Open the project and enable all the blocks in the FFmpNIST workspace file. Refer project documentation for details about the project. In CASP, a typical machine learning model starts with a neural network controller block. It generates required control signals to the dataset block and all the neural network blocks present in the model. Dataset size parameter value is configured based on number of data values present in the dataset file configured in the dataset block. Number of output stages parameter value depends on number of neural network blocks present in the model. Dataset block specifies parameters related to the dataset used to train the neural network. For current project, MNIST dataset is chosen as dataset type. The output port data size and label port data size depends on the dataset data and label data sizes. User has to specify the dataset data file path and label file path in this block. The dataset files shall be present in the project directory. The output of the dataset block is fed to the first feed-forward neural net block, FFNN0. The second output of the neural net controller block is fed to the two neural net blocks. After going through some processing blocks, the output of the label port of the dataset block is ultimately fed to backpropagation input port of second neural net block. Confusion matrix block calculates accuracy, precision and other parameters to estimate the performance during the neural net training. The two feed-forward neural net blocks are connected in cascaded mode. The first block is configured with one input layer with 784 neurons that is matched with the output of dataset block. It consists of one hidden layer with 64 neurons. Activation function used is leaky ReLU. Other parameters are configured suitably. The second feed-forward neural net block is configured with one hidden layer with 64 neurons that are matched with the output of the first neural net block. The output layer consists of 10 neurons that are matched with the label output of the dataset block. Other parameters are configured similar to the first neural net block. Set up simulation with suitable parameters and start the native simulation. As you can see, the simulation panel consists of sub-window 1 that plots accuracy, precision, sensitivity, and F-score from the output of confusion matrix block. Current data set sample index number is indicated in sub-window 4. Current data image is displayed in sub-window 3. The table indicates the predicted output from the neural net block and the actual label from the data source block for the current image. After some training, let's check the performance of the neural net. It seems that our simple neural network model predicted correctly for most of the input images. The CPU utilization is around 10% for an 8-core 16-thread processor. Let us increase the number of computational threads in CASP and try again. After the increase in threads, the training performance is considerably increased. The CPU utilization is also increased proportionally. Let us now do the same neural net training using Opencl across the 2 GPUs present in the native hardware. For this, Opencl platform index and device index settings shall be configured for the GPU to be used. Also, Opencl shall be enabled in the neural network block parameters. The GPU 0 utilization has increased, indicating that the current model is running on GPU 0. Similarly, we will enable GPU 1 and check its utilization. We will repeat the same process for CUDA on GPU 1. We will now perform the neural network training of the same model on Raspberry Pi 4 architecture. Raspberry Pi is updated with latest drivers and libraries, and is available on local network. We use VNC to make a remote desktop connection to this target. In CASP, change the target to Raspberry Pi 4 remote build and enter its IP address in remote build parameter. First we need to install CASP Remote Build Toolchain on the target. For this we need to generate Remote Build Toolchain and copy to the target. Enter target path of Raspberry Pi where this toolchain will be copied. Click on Generate button to generate the toolchain. After completion, the target toolchain folder will be created at the specified path on the host PC. Create a zip file of the folder and copy to the target. Also, copy the MNIST data set to the target. On the target, move these files to the Pi folder and extract the files. Move the MNIST folder to the build directory inside the toolchain folder. Open the README file from the toolchain folder and follow the instructions to install required dependencies on the target. The Qt5 and OpenCV libraries were already installed. We will skip these steps and move on to configure CASP for remote build. Open a terminal in the toolchain directory and type the commands as listed in the README file one by one. Do a sample test run of the CASP simulation panel to check whether the remote toolchain is configured properly. Run CASP or build file with local IP address. With this, CASP remote toolchain should be ready to accept commands from the host PC. On the host PC, set the target IP address in the remote build IP address parameter. Click Run button to build and simulate the model on the target. As you can see, the build process has started on the target. After the build, CASP simulation panel should start automatically. During the first time run, note the generated device ID of the target and enter the same in the target hardware ID of setup simulation parameters on the host PC. After entering the hardware ID, start the simulation again. Simulation has started on the target. After some training, let's check the predicted output versus actual values. The current model seems predicted most of the images correctly. We will now perform neural network training of the same model on Nvidia Jetson target by following similar steps. The target board is updated with latest drivers and libraries, and is available on local network. Select the target in CASP setup and enter the target IP address. Enable CUDA support. Generate remote build tool chain for the target. Create a zip file of the tool chain folder and copy to the target, along with the MNIST dataset. Move these copied files to the folder where it has to be installed and extract the files. Shift the MNIST folder to the build directory in the tool chain folder. Configure CASP remote build by following steps mentioned in the README file. The Qt5 and OpenCV libraries were already installed by using the procedure mentioned in this document. Test run the CASP simulation panel to ensure that it is properly configured with all the dependencies installed. Note the device ID and enter the same in the target hardware ID in CASP. Run the CASP or build application from the terminal with local IP address as argument. With this, target is ready for remote build. On the host PC, ensure the target is set properly and click on Run button to start the build process and run the simulation. Simulation has started on the target. Till now, our model is using GPU for its computations. Configure to use only CPU and try again. Seems our model is using CPU consistently now. After some training, our model seems predicting the images correctly now. Thank you for watching this video.